Okay, so we're going to look at graphing and solving equations involving the tangent, graphs, and functions. So two things you need to do. You need to be able to graph the tan function. You also need to solve for when a tan equation equals a certain value. So when we graph tan functions, always know what your basic tan x equals y looks like. Then similar to parabolas, we can change the width, height, starting point of tan functions according to the equation given. If we have y equals a tan brackets b plus cx plus d, a could reflect the tan graph if it's less than 0, and it also tends to stretch it vertically, or I guess slow the pace of the graph down or speed it up. This we normally don't really pay much attention to because the graph will always go towards infinity. Our b helps us tell the period. So because our general tan graph has a period of pi, when we transform the graph, it will have a period of pi over b, whatever that b is. C over b will tell us the shift and the horizontal shift. So whether it moves left or right. If you calculate C over B and it's a negative, that means you move it in the opposite direction. So the starting point will be towards the right. If that answer is positive, then you move your graph to your left. And of course, D is the vertical shift. Do we lift the original tan graph up or down? Once we've done that, we can solve equations by hand. We use our graph as a guide. Okay, then there are a few steps I'll take you through, including moving any numbers outside the tan function to the right-hand side. We solve the equation for just one angle, and we can normally use trig to do that, or one value of x. Okay, and then we add the period to this until we find all of the values for x within the specified domain that solve the function. First example. Okay, graph the function 3 tan 2x equals y. So the x is kind of like your theta in this case. So I like to write it all out and make sure that it's of the form y equals a tan bx plus c plus d. In this case, I don't have a c value, or it's 0, and my d value is also 0. This will just help me figure out how the graph is shifted. So the a is 3. This means that it stretches. So the graph climbs to infinity faster, but we don't normally show this on the image. It won't really affect how you draw it too much, which is nice. If it was negative, then we would reflect it. That would affect the image a lot. Okay, the period comes from my b value. So the period is pi over b, or pi over 2. That means it takes pi over 2 units to begin again, pi over 2 units to begin again, and we keep adding on those pi over 2 units. There's no vertical shift because d is 0. There's also no horizontal shift because c over b, well, that would just be 0 over 2, which is 0. So then that's nice. I know the starting point of my graph. Because there's no vertical or horizontal shift, the starting point of my graph will be 0, 0. There's one more thing that's good to know, and that's where the asymptotes are. So remember, a tan function is normally sine over cos, and asymptotes occur when that cos function is 0. So in this case, we just say the asymptotes occur when cos of bx plus c, whatever it is for our particular function, equals 0. So we have cos, my bx is 2x, I don't have any c, so cos 2x equals 0. Now, I know that cos 2x is 0 when my theta value, or my 2x, is pi on 2. So if I have 2x equals pi on 2, just rearrange it, and I'll get x equals pi on 4 units. So every pi on 4 plus the period units, because remember those asymptotes will repeat periodically, and my period is pi on 2. So every pi on 4 plus pi on 2 units, okay, there will be an asymptote. Now I think I'm good to draw it. So I'm only going to draw it between 0 and pi and see what happens. I'm going to start at 0. I know the starting point is 0, 0. My first asymptote is pi on 4. It's next going to hit the origin, and then it's going to have another asymptote, pi on 2 periods after pi on 4. So pi on 4 plus pi on 2, I think that is 3 pi on 4. So my graph's going to keep going a little bit longer. Now let's have a look at where it hits the x-axis. So remember that will happen every pi on 2 units. So I'll have it at 0, at pi on 2. And if I plus another pi on 2 here, I should get pi. So this is the graph of the function between 0 and pi. So once we've graphed the function, now we have to solve the equation. So we have 3 tan 2x equals root 3, and we're just solving between 0 and pi. Here are the few steps that we have to take to be able to do this. Step number 1 is to move all the numbers surrounding the tan 2x function to the right-hand side. I already have the root 3 over there, which is great. So I've just got to move that 3 at the front to the right-hand side as well. Once we do this, we'll get tan 2x divided by 3 for both sides is root 3 over 3. Your second step here is now to solve for x. And just a little side note, that root 3 on 3 is the same thing as 1 over root 3. That might help when you're drawing your triangles for the next step. So let's solve here. I just need to find one solution to this equation. So I'm going to draw a triangle to help me. Let my angle be 2x. And then if it's tan, I know the opposite side was 1, and the bottom side, or the adjacent, was root 3. And I can figure out the length of the hypotenuse. That will just be 2. This looks very familiar to a triangle where I know what the values are of the theta. So if I divide everything by 2, I end up with my unit triangle. I have my hypotenuse is 1. My opposite is half. My adjacent is 1 root 3. And I know the angle opposite, if I've memorized it, be a half if pi on 6. So that gives me one solution, that 2x has to be equal to pi on 6. But I really want to find a solution for x, so let's divide by 2. I'll get x equals pi on 12. Step 3 is to find all solutions. So that is only one solution. There might be more for our equation between the domain x is within 0 and pi. So remember that the solutions will occur every period. So we have to have x equals pi on 12, but we're going to keep plussing on a period or subtracting a period to find all of the answers. So we can write our general solution as x equals pi on 12 plus k pi on 2. Pi on 2 was our period for this function that we saw in the previous slide. And then k is just some number, 0, 1, 2, minus 1, etc. If k equals 1, we get x equals pi on 2 plus pi on 12. And this will be a solution if it falls between 0 and pi. So we end up with 7 pi on 12. Now that is smaller than pi, bigger than 0, so that's probably going to be another solution. If I try k equals 2, I get that x equals pi on 12 plus 2 pi on 2, or pi on 12 plus pi. Now that is outside our restricted domain between 0 and pi. So that will not be a solution. Our only solutions will be the two we found before, pi on 12, right, because that's between 0 and pi, and 7 pi on 12. We don't need to keep testing values because we've got all the values that will lie between 0 and pi. The last thing you can do is check this in your graph. As you can see in our graph, I've drawn a little red line here where 3 tan 2x equals root 3. And I can see that I think I'm going to get two solutions where that graph crosses root 3. And just like our answer says, we did indeed get two solutions.